Hello everyone, in this lesson we're going to be talking about linear inequalities. So a linear inequality is a statement of inequality between two variables that are in a linear relationship. And the feasible region is the collection of all points that satisfy or make true all of the inequalities or equations. So let's look at an example. It's a word problem situation, and we've got actually a graph of a linear inequality already done for us, and so we're going to try to connect the two here. So number one says, Sarah goes to the store to buy apples and oranges. Apples cost $3 and oranges cost $2. Sarah must spend less than $30. The graph below, or I guess to the right here, shows all the possible combinations of apples and oranges she could buy. Write a linear inequality to represent Sarah's purchasing options. So what does it mean that this represents all possible combinations? So for instance, I see that there's a point right here, and that's the point 5, 5. So that's 5 apples and 5 oranges. Well, 5 apples would cost $15, and 5 oranges would cost $10, so that's $25. So that's a combination Sarah could purchase. If we pick another point, like this point here, that is 2 oranges and 7 apples. Well, 7 apples cost $21 and 2 oranges cost $4, so 21 and 4 is 25, so that one works. But if we looked at a point like even this one right here, that is 8 oranges and 6 apples. 6 apples cost $18 and 8 oranges cost $16. So 18 and 16, that's more than 30, so that does not work. So in this way, this is a representation of all the possible points. So we'd also like to create a inequality statement that accomplishes as well. So let's define our variables. A equals number of apples. And please don't let O equal oranges. We're going to let B equal the number of oranges. So this is kind of in a standard form setup, like some of the word problems we did with just equations before. So we've got 3 apples plus 2 oranges, and that's got to be less than 30. And so we're going to talk about how we can go from this equation to this graph in a moment, but we can see the equation and a visual that kind of represents all the possibilities. This shaded region is what we call the feasible region. Let's look at another example. So it says Dan needs at least $210 to buy the new iPhone 6. To make some extra money, he plans on selling his old PlayStation and Xbox games. Each Xbox game he sells earns him $30, and each PlayStation game he sells earns him $15. The graph to the right shows all the possible combinations of ways he could sell his video games to earn the money. So again, let's just look at a point real quick. For instance, this point right here, that's 5 Xbox games and 10 PlayStation games. Well, it says Xbox games are 30, so 5 times 30 would be 150, plus he's going to get 15 for each of those PlayStation games, so 10 times that is another 150. So that would be $300, and that's at least the 210 he needs. So this is another point that works. There are many others. So the linear inequality, and we'll go ahead and say x equals number of Xbox games, and y equals the number of PlayStation games. We could say that 30x plus 15y, okay, at least $210. That means this is the money he's earning has to be greater than or equal to. It could be $210 because at least could be that, so $210. Okay, so let's put some of these pieces back together to figure out how we can go from the inequality to the graph. So we'll take away the word problem for a moment and just look at the situation y is greater than 3x minus 1. So the first step is that we're going to graph the inequality as if it was an equation. One caveat to that, if the inequality is a less than or greater than, we are going to use a dashed line. If it is a less than or equal to or greater than or equal to, we will use a solid line. We'll see what that looks like in this example. So this one is a greater than or equal to, so we're going to use a solid line, and we're going to graph it just as if it was an equation. So this graph starts down 1, and goes up 3 over 1. And we can find some more points here to complete our graph. Great. Okay, so we'll connect those points with a nice solid line. Okay, the next step is to find the feasible region. How do we do this? We determine if a test point is true or false. And we use the test point to determine the feasible region. One of the best test points is 0, 0. It's basically a point on one side of this line that we've graphed, and if we test it and it's true, that's where all the true values are going to be. So let's go up to our equation. We're going to be using the point 0, 0. It's so nice because it simplifies everything. 3 times 0 is 0 minus 1. So we have really that is 0 greater than negative 1. Is that true? Yes, that's true. So where is this point on our graph? Let me change colors here. This point here is true. So that means that all of our true points are on this side of the line. So we'll go ahead and shade these in. You can, use, the side of your pencil. You don't have to obliterate it like this. If you have a highlighter, that can be nice. Digitally, I can go ahead and use the highlighter tool. It works out pretty nicely there. You don't have to be, 100% perfect. I'm not really concerned. I'd be even fine if you just did something like that as well, just to show that the feasible region is on that side. And that is, the step 3 is to shade the feasible region. If we got a point that is false, we would shade the other side, and we'll look to see that happen here in a second. Okay, so let's try another example. So for this next one, y is greater than or equal to negative 3/5 x plus 3. So we'll start by plotting the y-intercept, and we'll go down 3 and to the right 5. Great. We can go up 3 and to the right 5 this way again. Now we look at the symbol here. This is telling us we need a solid line connecting these points. All right, so we put our solid line there, and we're going to test out 0, 0. So 0 greater than or equal to, this is all going to be 0 plus 3. Is 0 greater than 3? No, that's wrong. So this point here, the origin, that was our test point, 0, 0. That's false. So we don't want to shade that side where the test point is. We want to shade the other side. So in this case, the test point was false, we shade the other side. If the test point's true, we shade the side it was on. Okay, let's look at another example. Here we've got y is less than negative 2/3 x plus 3. So we start up 3, and we go down 2 and to the right 3, down 2 and to the right 3, and we can do this in the other direction. Up 2 and to the left, oops, that's one too many. 3, up 2 and to the left 3. Great, but this time, because we have just a less than, we're going to make a dotted line. Dotted, dashed, however you want to describe it. So, dotted. And why is this? Well, as we said, we're shading the possible answers. So, if we were to look at a specific point on this line, let's say we took this point right here. It's right on the line. That's the point, negative 3, 5. Well, is this point true? So we've put in 5 for y less than negative 2/3 times negative 3 plus 3. Okay, here these cancel and the negatives cancel, so we have 2. So we have 5 is less than 2 plus 3 is 5. Is that true? Nope, that's a false statement. So it's so close, right? It looks like it's almost true, I suppose, but it's a false statement there. So the dotted line is representing that the points on this line are not part of our feasible region. Okay, so let's go back and find a test point that's not on our line. We like 0, 0 the best. 0 is less than, this will all be 0, plus 3. Is 0 less than 3? Yeah, sure it is. So here's our point. It is true. So we go to shade, and we will shade all of this region down here. Great. Let's just look at some other examples that are not in slope-intercept form. So if we look at these examples, if I look at number 11, for instance, you could try to graph this by the intercepts, but right away, if I notice this, I'm going to notice that the one intercept is way off of this graph space. So the other way to graph when they're in standard form is to put them into slope-intercept form. So I'm going to subtract x from both sides, 4y is less than negative x minus 20. Divide by 4 in all three places. And we get y is less than negative x divided by 4 is the same as negative 1/4 x minus 5. Terrific. Now we have a slope-intercept form equation, inequality in this case, and we'll go down negative 5, and we'll go down 1 and to the right 4, up 1 and to the left 4. We look at our inequality symbol. It is less than, so we have a dotted line. So we'll connect those. 1, 2, 3, 4. Okay, a couple of dotted line segments there. Okay, it's time to look at a test point. So I love 0, 0. Is 0, 0 going to be true or false? So that would give us 0 less than, this would be 0, negative 5. Is 0 less than negative 5? Nope, that's false. So we're going to shade the other side. There is one time where you can't use 0, 0 as a test point, and that would be if your line goes right through 0, 0. If it goes right through 0, 0, testing 0, 0 won't help you. You wouldn't know which side to shade because the point is right on the line. So then you'd have to pick just any other point on one side or the other. And that's how you graph linear inequalities.